A very good afternoon to everyone. We'll be now presenting our final project, which is autonomous UAV landing on a moving platform. I am Ishwarya and my teammates are Ishita and Kshitij. Over the past few decades, the demand for unmanned aerial vehicles have increased significantly due to the current events and pandemic. But there has also been significant improvement in the design and structure of these aerial vehicles. Now, coming to our problem statement, these vehicles have a very limited range and are not suitable for traveling long distances. Furthermore, increasing payload decreases their ranges. Whereas for the ground vehicles, they provide good long distance coverages, but they are not very ideal for stop and go scenarios due to the wear tear or low gas mileage. Traditionally, a lot of work has been done on landing these autonomous UAVs on stable platform. Industry and market standards such as marker-based landing and RTK have been very prevalent. But these scenarios do not cover all the area of operations where the drone needs to be landed on a mobile platform.
Through this project, we designed an approach wherein the ground vehicle navigates through the neighborhood, which can be used for delivering heavy payloads. The drone or the aerial vehicle carries lighter payloads and delivers at respective locations and then returns to the ground vehicle to pick new payloads. This is also representing a mobile hub and spoke model used in commercial sectors. Here we present the implementation of UAV landing on a mobile platform, which is a ground vehicle in our case. This method can be implemented for last mile delivery as well. Drones in recent years have been widely used in a number of different areas like security, healthcare, and commercial sector, where they can be used for surveillance and transporting essential goods. The reason for the increased application is because they can be deployed quickly and are cost effective. There are a number of factors to look into while landing on a moving platform, which involves landing zone, flying trajectory planning, and robust control configuration.
Now, as for the tech stack, we're using Gazebo to simulate the world and the actors, ROS as the communication backbone, and its plugins like PX4, Mavros, and SITL to control the vehicles. To give you a system overview, we have the simulation that talks to our nodes. We have two of them, one that controls the UAV and the other the UGV. The coordinator reads the positions of both the vehicles from the simulation, calculates the trajectory of the UAV, and sends it to it. The UAV runs in the position control mode, whereas the UGV is in velocity control mode. Both these vehicles do not talk to each other, and the UGV acts independently irrespective of what the coordinator has to say.
We will now be presenting a breadth of different scenarios. In this scenario, we showcase a scene where UAV starts off very far away from the UGV.
Here is another scenario where the drone takes off close to the UGV and lands on it.
In the third scenario, the UAV retries its landing after looking for a better opportunity to land.
During the project, we faced several setbacks. Some of them were related to generating the simulation, communication with the UGV and the UAV, and defining the trajectory for the UAV that best suits our application to land on a moving platform. Some future prospects for this project include obstacle avoidance for the drone, a tiered approach for localization and path planning using a mix of sensors like GPS, V2V communication, 5G, millimeter wave, LiDAR, and or cameras. One could use reinforcement learning to find trajectories for the UAV. Lastly, we could also implement a route planner that maximizes productivity and minimizes the cost.
Thank you, and we're open to questions now.